So far we've looked at matter, so leptons and quarks. There is another class of particles which make up the Standard Model, and these are called the mediating particles. And these are particles that can be used to explain the fundamental forces. Now, there are four fundamental forces in the Standard Model: gravitational, electromagnetic, and then two nuclear forces, right? The weak nuclear force and the strong nuclear force. So gravitational forces should be fairly familiar with from the gravitation topic. Electromagnetic, we'll do a wee bit more about waves and so on, but these are basically to do with light, so electromagnetic radiation uh, and so on. But the ones I'll concentrate mostly on here then are the nuclear, and the weak nuclear force is involved in beta decay, and the strong nuclear force, as we'll see in a wee second, is about keeping particles together, keeping the nucleus together. So these particles can be used to explain forces. It's just one way of modelling forces. Basically, they're called exchange particles, where the two objects involved in the force kind of throw the particle backwards and forwards between themselves. But really all you need to know then is basically the idea of which force goes with which particle. So gravity acts on masses as the weakest force, but has infinite range. So when we're looking at cosmology, for instance, it's the most important force because of its huge range. The electromagnetic interaction affects all charged particles, and its force-mediating particle is a photon. Incidentally, the graviton is the force-mediating particle of gravity, but it's kind of doesn't fit well into the standard framework just now, so you'll see it included in some frameworks, but not others. The electromagnetic force has also got an infinite range, but over larger range it doesn't tend to be significant, because when you look at things like planets, their overall charge is close to zero, and therefore you don't get significant forces over huge distances. The weak nuclear interaction can interact with both quarks and leptons, and is responsible for beta decay. And the strong one, the force-mediating particles for the weak nuclear reaction, it's actually got three force-mediating particles called W plus, W minus, and Z naught. And it's, as its name would suggest, it's very much weaker than all the other forces involved at nuclear distances. But the strong force is the one we probably discuss most, and it's what attracts quarks to each other. So if you think about the proton, you've got two positive charges in there from the two up quarks. They should really be repelling away from each other. The proton should be flying apart. And the reason it doesn't is the strong nuclear force holds the quarks together. And that works for both baryons and mesons, regardless of the electrical charge in them. So it's a force that always acts between quarks. It's always attractive. And you also, because of that, get some residual effect between neighbouring nucleons, so neighbouring protons, neutrons, etc. And that's what holds the whole nucleus together. So, the positively charged protons don't fly apart between them. So the force-mediating particle for strong interaction is called the gluon. Incidentally, you also hear these force-mediating particles called bosons. Okay, just you come across that phrase as well. And it's called a strong force because it's much stronger than the electromagnetic repulsion that we've just been talking about over very small nuclear distances. The strong force increases with distance, which is why it's hard to pull these protons apart, for instance, to split the atom, basically, split the nucleus of the atom. But once it gets beyond a certain distance, it decreases dramatically beyond that. Right, so it really only acts over very short nuclear distances and is negligible beyond that.